Welcome back everybody to episode 5 in the openStars video series. This is a series where we're talking about basic stellar astronomy, and as we go along we are demonstrating important concepts by doing experiments with the grayStar 3 virtual star simulator. In the first 4 episodes in this series we learned a lot about 5 quantities that are basic stellar properties. And taking them in order, we have a star's effective temperature, which you can also think of as being its surface temperature. That's what we talked about in episode 1. We have the mass and the radius of the star, which we talked about together in episode 2. We have the star's surface gravity, expressed as a log g quantity, which we talked about in episode 3. And then we have finally the star's total luminosity, which is an expression of the star's absolute brightness. And we talked about that in the last episode, episode 4. So there's actually a couple of different ways that you can think about these 5 quantities. On the one hand, you can think of them as being measurable properties that characterize a star. Although, as we have seen, some of them are more straightforwardly measurable than others. In particular, effective temperature and surface gravity are relatively straightforward quantities to measure. Astronomers can routinely measure them for any star of interest. The other 3 quantities, mass, radius, and luminosity, are harder to measure. You have to work harder, although they can be measured in principle. Another way that you can think about these 5 quantities is that they are also basic stellar parameters that tell us what type of star that object is and what it will look like when we observe it in various ways. So in this video, we are not going to introduce anything fundamentally new. We're not going to talk about any more basic stellar properties or parameters. We've already covered all the ones that we need. What we're going to do in this video is we're going to put everything together and look at the big picture. And what I mean by that is we're going to talk about what happens if we go out and measure or somehow otherwise determine these properties for lots of different stars, a big representative sample of stars of all types. Okay, and if we do that, then what does that tell us? What do we learn about nature? Now, if we were to do that, if we were to go out and measure some or all of these 5 basic properties for lots and lots of stars, say hundreds or thousands of stars, then of course that would present us with a lot of information, a lot of data that we would need to somehow sort out and organize. It turns out the best way to organize that information in order to gain insight is to plot stars up in a diagram where we plot them up according to one of their basic properties versus another one of their basic properties. And it turns out the best sort of diagram for doing that is something called an HR diagram. Now I'm going to be telling you all about the HR diagram in this episode and what those letters HR stand for. But before we move on and do that, let me just point out to you that in the output area of grayStar 3, there actually is a very simple HR diagram. So this is the diagram that we're going to be talking about today, and what's more, grayStar 3 actually plots up the star that it's simulating in this simple HR diagram. Of course, remember that by default, when grayStar 3 first loads, it is simulating the sun. That's the sun that we're modeling here. And so what grayStar 3 is doing is it's plotting up a simulation of the sun in this little simple HR diagram. Now, at the end of this episode, I'm going to come back to this simple HR diagram that grayStar 3 includes in its output area and say more about it. In particular, I'll tell you about a fun and informative pedagogical activity that students could do using grayStar 3's built-in HR diagram. I also want to point out here at the very beginning that the HR diagram is really the pedagogical capstone of the first 5 videos in this series. If you are a teacher or an instructor and you're thinking about preparing a major unit on stellar astronomy, then a great goal is to bring students to the point at the end of the unit where they can understand and appreciate the HR diagram. That's a wonderful way to tie everything together and to wrap everything up, and an important thing for students to understand. So it's really the ribbon around the whole package. So what I'm going to do is click on the link here, and that will take us to a much more detailed and elaborate version of the HR diagram, and this is the diagram that we'll be working with throughout most of this episode. The full name of this diagram is actually the Hertzsprung-Russell diagram. That's what the letters HR stand for. It's named after the two astronomers who first realized the significance of this diagram. Hertzsprung was a Danish astronomer, and I tried to find out how to pronounce his first name, but was unable to do so, so I'm not even going to try. And Henry Norris Russell was an American astronomer, and they were both working in the early 20th century. So Hertzsprung-Russell diagram is a mouthful, so people just routinely call it the HR diagram, and sometimes they just abbreviate it HRD. The wonderful thing about the HR diagram is that it's actually a surprisingly simple idea. It's actually not very difficult to understand how to construct the diagram. However, it has proven to be an extremely important diagram. It is without argument the single most important diagram in all of stellar astronomy, and it's arguably one of the 2 or 3 most important diagrams in all of astronomy, period. By looking at the patterns that stars make when they are plotted in this diagram, astronomers have been able to gain a lot of insight into the deep hidden interior of stars, something we haven't talked about in this video series, and also insight into how stars change with time as they age, the subject of stellar evolution. Let me also zoom out here just for a second so you can sort of see the big picture, what we're talking about with this diagram. Now, when one is first confronted with the HR diagram in all its glory, it's kind of complicated. There's sort of a lot going on here to sort out. So what we're going to do is we're going to take this in stages and introduce groups of stars one at a time. So what I'm going to do to begin with here is I'm going to come up to the top, and I'm going to uncheck some of these boxes here so that we take all the stars out of the diagram and we are starting with a blank slate with an empty diagram. I'll just zoom back in again here. And by the way, the ability to do that, to turn individual groups of stars on and off in the diagram, actually makes this particular version of the HR diagram an especially useful one for teaching. The HR diagram is a two-dimensional plot, and so it has a horizontal axis or an x-axis and a vertical axis or a y-axis. And we're going to take these in order, so let's start off by talking about the horizontal axis or the x-axis. Now, we said that the HR diagram was going to be a plot of one of a star's basic properties versus another, and the basic property that we are plotting up on the horizontal axis is the star's effective temperature, which you can also think of as being the star's surface temperature. So that's the quantity that we talked about back in episode 1. Now, there are a couple of twists here. The first twist is that by convention, the horizontal axis is backwards. That is to say that the effective temperature increases to the left rather than to the right. Okay, so when we put stars in this diagram, cool stars are going to go to the right and hot stars are going to go to the left. Now, the next thing to notice is the unit of temperature here. We are on the Kelvin temperature scale, also known as the absolute temperature scale, and that's the temperature scale that we defined back in episode 1. It's also worth noting the range of effective temperature here because this sort of gives us a clue to the range of effective temperatures that astronomers have measured among stars. So we're going all the way from a value of about 32 or 3300 Kelvin here on the right. So that's about the lowest effective temperature astronomers have measured for objects that we normally recognize as stars. And then on the left, we're going all the way up to about 50,000 Kelvin or so. So that's about the hottest objects that astronomers have found and measured. Now already, if we think back to episode 1 and the relationship between effective temperature and color, we can also guess where stars are going to go in this diagram according to their color. That red stars are going to go to the right, blue stars are going to go to the left, and yellow stars will end up in the middle somewhere. Okay, well, the other twist that I want to tell you about with this horizontal axis here has to do with the way these temperature tick marks are labeled with temperature values. So first of all, these tick marks have a uniform spacing in terms of the number of pixels of screen width that they have between one tick mark and the next one. However, if you look at the temperature labels on here, you will see that the temperature spacing from one tick mark to the next is not uniform. That over here on the right, the temperature increases from 3250 to 6500 Kelvin, so that's an increase of 3250 Kelvin from one tick mark to the next. Whereas over here on the left, from one tick mark to the next, the temperature jumps from 26,000 to 52,000 Kelvin. So that's an increase of 26,000 Kelvin. So the spacing in temperature value here between adjacent tick marks is certainly not uniform. That the spacing between adjacent tick marks corresponds to increasing intervals of temperature as you go from right to left. Now what's happening here is that we are using logarithmic scaling for these values. That these tick marks are labeled with values that are equally spaced in the logarithm base 10 of the temperature rather than the temperature itself. And the reason for that is because significant differences in properties between stars really depends on the difference in the star's relative temperature rather than the absolute temperature. That over here on the right hand side of the diagram, where stars have effective temperatures of say only 4 or 5,000 Kelvin, a difference between two stars of 1,000 Kelvin is a big deal. A 5,000 Kelvin star is quite a bit different from a 4,000 Kelvin star. Those are two very different objects with quite different properties. A change of 1,000 Kelvin over here is a large relative change. On the other hand, over here on the left-hand side among the hot stars, a difference between two stars of 1,000 Kelvin is not very significant. That's a very small relative change. A star whose effective temperature is 27,000 Kelvin is going to be almost indistinguishable from a star of 26,000 Kelvin. So if we were to label these tick marks with linear temperature differences in the ordinary way, what would happen is that all the cool stars where things are changing fairly rapidly with temperature would all get scrunched up together over here against the right hand edge of the diagram, and most of the space in the diagram would be taken up by the hot stars where things change very slowly with equal increments in temperature. And so that wouldn't be very useful. So what we need is a scale that stretches out the right hand side of the diagram among cool stars and compresses the left hand side of the diagram among hot stars, and that's what this logarithmic scaling does. So finally, the last thing that we want to notice is where the sun lies along this horizontal effective temperature axis. Remember, the sun is an important primary reference object. We always want to understand other stars by comparing them to the sun. And from video 1 and throughout this series, you may remember that the sun's effective temperature is 5,800 Kelvin. And so you can see where the sun lies here. It's marked in the diagram. It lies sort of between the middle and the right hand side of this diagram, right here. Now let's turn our attention to the vertical axis, or the y-axis. Now notice that in this particular HR diagram, the vertical axis is actually double labeled. There are two vertical axes here. We're only going to be using the one that's on the left, the leftmost axis, the one over here that I'm indicating. So just ignore this other axis, both its label and its values, and let's just think about the outer axis here, or the one that's leftmost. The basic stellar property that's being expressed here is the star's total luminosity. That's the quantity that we use to express the star's absolute intrinsic brightness, and that is the quantity that we discussed in episode 4. Now, you might also remember that astronomers refer to total luminosity as the bolometric luminosity, so that's what this symbol here, L subscript bol, stands for. Bol stands for bolometric, but that's just the astronomer's way of indicating total luminosity. Okay, so the vertical axis actually behaves in the way that you would expect, in that it increases upwards. So we have total luminosities increasing as we go upwards along this axis. So when we enter stars into this diagram, stars that are intrinsically bright will go towards the top of the diagram, and stars that are intrinsically faint will go towards the bottom. Now what about the units of total luminosity? Now remember, luminosity is brightness power or radiation power. So if we wanted to be on the metric system on this vertical axis, we could use units of watts. However, to make things more meaningful, what we're going to do instead is use solar units, and we are going to mark these axis labels in units of solar luminosities. Okay, now the next thing to note is that once again, the vertical axis here, the luminosity axis, is logarithmic rather than linear. Now these tick marks are not equally spaced in pixels along this axis for various reasons having to do with how this plot was made. But be that as it may, the point is here that if two tick marks are equally spaced from one another in pixels going up this axis, then they are not equally spaced in luminosity, rather they are equally spaced in the log of the luminosity. And what that does, once again, is it stretches out the bottom of the plot where the faint stars are, and it compresses the top of the plot where the bright stars are. Otherwise, all the faint stars would be scrunched together at the bottom of the plot, and we wouldn't be able to see what's going on. Now there's an important difference here between the way things work on the vertical axis and the way they do on the horizontal axis. In particular, on the vertical axis, these tick marks are actually labeled with the log of the luminosity, not with the luminosity itself. So that's important to keep in mind. So let's just look at an example here to make sure we understand what this means. If we pick, say, on this tick mark here that I'm indicating with the arrow, it's labeled as having a value of 1.1. So what does that mean? I guess it's not going to let me highlight that. There we go. Does that mean that the luminosity indicated by this tick mark is 1.1 solar luminosities? No, it does not. What it means is that this tick mark corresponds to 10 to the power of 1.1 solar luminosities. So that's a value that's a little bit bigger than 10 solar luminosities. Okay, so that's an important thing to remember about how these values work on the vertical axis, and we'll actually come back and look at this again when we discuss the range of the axis. So another important thing to keep in mind about the vertical axis here is that it is luminosity. And remember, luminosity indicates a star's absolute intrinsic brightness, not its apparent brightness. And that's important to remember, that if you think back to what we talked about in episode 4, when we look at an image made from Earth like this one, the brightnesses that you see in this image correspond to apparent brightness as measured here at Earth, not absolute brightness. And a star's apparent brightness depends on a combination of both its absolute brightness and its distance from us. Okay, so it's important to realize that The luminosity that we're plotting on the vertical axis here is the star's absolute brightness. If we were to try to plot stars up according to their apparent brightness in this diagram, it would just make a mess, because where a star goes in the diagram would depend on its distance from us as well as its absolute brightness, and that would make it very difficult for us to see any order among the stars in this diagram. Okay, so we're plotting up absolute brightness here vertically, and that is a quantity that is independent of distance. The star's distance from us does not play a role in where it goes in this diagram. Okay, so once again, before we go any further, it's useful just to think about the range of values along this vertical axis here. So let's start at the bottom. That this is a clue to the range of luminosities that astronomers have measured among stars. And note that the smallest value that we accommodate here is -2. So what does that mean? That means that down here at the bottom we have stars that are as faint as 10 to the power of -2 in solar luminosities, and so that's 1/100th of a solar luminosity. At the other end of the range here, up near the top, we have a value of 5.9. We can just round that up and call it 6. So that means that the brightest stars we need to be able to accommodate have luminosities of 10 to the power of 6 solar luminosities. So that's 1,000,000 solar luminosities. So let's just take a moment here to think about the enormous range of luminosity that we have along this vertical axis here in this diagram. That we are going all the way from stars of 1/100th of a solar luminosity up to stars of 1,000,000 solar luminosities. And so that's a range of 10 to the power of 8, or a range in which the brightest stars are 100 million times brighter than the faintest stars that we need to accommodate. Okay, and that's just the range that astronomers have measured. In fact, if we think about what we discussed in episode 4, maybe that's not so surprising. That after all, a star's total luminosity varies as its effective temperature to the power of 4. And so remember, that means that modest changes in effective temperature correspond to huge changes in luminosity. So in a way, it really shouldn't surprise us that we need to have a luminosity axis that covers a huge range in luminosities, even though the range in effective temperature isn't really that big. So the last thing that we want to think about once again is the location of the Sun along this vertical axis. That's our primary reference object. And you might notice if you read across here that the Sun is at a value of exactly 0 on this vertical axis. Now, does that make sense? Well, this allows us to get a little bit of practice here thinking about logs. In solar units, the sun's luminosity, of course, is 1 solar luminosity by definition, and the log to base 10 of 1 is 0. If you take 10 and raise it to the power of 0, 0 powers of 10 is equal to 1. So on this logarithmic axis, the sun's position is 0 in the log of the luminosity in solar units. So at this point, we've done a pretty good job of setting up and defining our HR diagram. So now we are ready to populate it with stars and see what happens. So I'm just going to zoom out here a little bit so that we can see a bit more of the big picture. So to populate this diagram, what we want to do is go out and carry out a census or a survey of stars, where for each star in the survey, we are going to start off by doing some photometry and measuring the color of that star, and then using the measured color to determine the star's effective temperature, just like we talked about back in episode 1 in this series. And so once we've determined the effective temperature of the star, that tells us where the star belongs along this horizontal axis in the HR diagram. Then we can go back and measure the star's flux as intercepted by a detector here at Earth. That tells us the star's apparent brightness. And if we also have a way of determining the distance to that star, then we can combine that with the apparent brightness to determine the star's luminosity. And that will tell us where the star belongs along this vertical axis. And so combining those two pieces of information, we can determine where the star belongs in this diagram and we can plot it up. Now our goal here is to find out where stars fall in this diagram when we look at them very generally. And so presumably the most complete and accurate way for us to do that would be to go out and survey the total population of stars. That is, every star in the universe, or at least every star in our own galaxy, the Milky Way galaxy. However, as you can imagine, that's actually not possible practically. Even our own galaxy, the Milky Way, contains something like 100 billion stars. So that's 10 to the power of 11 stars, and for most of them, we cannot make these observations. That most of those stars are just too far away, and so they're too faint, or they are obscured by interstellar dust that lies in our galaxy, or they may be in very crowded star fields where we cannot separately distinguish the stars from each other in order to measure their properties. These days, astronomers can probably make these measurements reliably and plot the stars in the diagram for, let's say, something like 100,000 stars. Now, 100,000 stars is a pretty big sample, but it's only about a millionth of the total population of stars in our galaxy. However, that's okay though, because we can still get an accurate picture of where stars lie generally as long as the sample that we can measure and plot up has the properties of being significant and representative. So let's just talk about this for a minute, because this is pretty important, and this is the kind of thing that astronomers need to worry about all the time whenever they go out and survey objects for their properties. So first of all, what does it mean for a sample of stars to be representative of the total population? Well, that means that each type of star that's present in the total population is also present in the sample. And it also means that if a certain type of star is very abundant in the total population, then it's also relatively abundant in the sample. And if a certain type of star is very rare in the total population, then it's also rare in the sample. So that the sample has the same demographics as the total population. That means that the sample is representative. And that's related to the second idea, which is that the sample should be significant. And what significance means is that the sample is big enough, it contains enough objects that it's not likely to be skewed by the random chance of which stars happen to be included in the sample and which stars not. As you can imagine, if we try to fill in this diagram by only measuring 10 stars, that would not be a very representative sample. That with only 10 stars, the odds would be pretty good that certain types of stars would be overrepresented or underrepresented greatly just by the random chance of which stars happen to be included in that sample and which not. On the other hand, if our sample contains more like 100,000 stars, then the odds that this sample will be skewed by the random chance of which stars were included and which not is pretty small. So some of these ideas may sound a little bit familiar to you when people who do political polling and market research survey people. They have to worry about the same issues. Is their sample representative and significant? Now, before we actually put a sample of observed stars into this diagram and look at the actual result, let's prepare ourselves and have a little bit of fun by making a couple of predictions about what we might find. As you may know, prediction plays an important role in the scientific method, but more importantly than that, making a couple of predictions is a way of preparing ourselves to make it easier to understand what it is that we're about to actually see. That even if the predictions that we make are wrong, those predictions will still serve as important reference cases for comparison that will help us interpret the actual result. Now we're going to make two predictions. I'll call them prediction 1 and prediction 2. So let's start off by talking about prediction 1. And Prediction 1 is inspired by looking at an image like this one, a representative image of a random star field. So when we look at an image like this, we might notice that we are seeing stars of all the various different colors, red, yellow, and blue. And of course that means that we are seeing stars with a full range of different effective temperatures. So that's the quantity that we're going to be plotting up on the horizontal axis of the HR diagram. Now for each of these colors, or each of these effective temperatures, we might notice that we are seeing stars of all of the full range of different brightnesses. So for example, among red stars, we have red stars that are bright, like this one, and we have other red stars that are faint, like this one down here. And the same thing is true for the yellow and the blue stars. So for stars of each color or effective temperature, we are seeing the full range of brightnesses. Now we do have to be careful though, because of course what we're seeing in this image is apparent brightness or flux, whereas what we're going to plot up in the HR diagram is absolute brightness or luminosity. However, those two are related by the distance, remember. So if we assume that these stars have a random distribution of distances, and that stars of each effective temperature have a random distribution of apparent brightnesses, then we might guess that at each effective temperature stars have a random distribution of luminosities. In other words, what we might guess is that nature is just as likely to make stars with every combination of effective temperature and luminosity. And we might even justify that by imagining that the process whereby nature makes stars may be very chaotic and very random, and so that process may be just as likely to result in any one combination of luminosity and effective temperature as any other combination. So on the basis of that hypothesis, what we would predict is that in the HR diagram, stars should be scattered uniformly everywhere throughout the diagram. Right? That if nature is equally as likely to make bright hot stars or faint hot stars or bright cool stars or faint cool stars, then we should find just as many stars in any one quadrant of this diagram as in any other quadrant, in which case stars should be scattered uniformly throughout this entire HR diagram. So that is our prediction 1. And if we didn't know any better, prediction 1 is actually not an unreasonable guess. Now for prediction 2, we might start by noticing that the quantity that we're plotting on the y-axis is the star's total luminosity, and the quantity that we're plotting on the x-axis is the star's effective temperature. Now if we think back to episode 4, we might remember that in that episode we learned that there is actually a mathematical relationship between those two quantities for stars, that a star's total luminosity varies as its effective temperature to the 4th power. So there's actually a mathematical relationship among stars between the quantity on our y-axis and the quantity on our x-axis. And so on that basis, we might predict that every star in the universe should lie along a common line in the HR diagram, namely the line that you would get if you were to plot up the function y equals x to the 4th power plus or minus some constant. Okay, now you may realize that that prediction is probably a little bit too simple, because once again, if we think back to episode 4, the other thing that we learned is that a star's total luminosity also depends on the star's radius. It depends on the radius squared. Now, radius is not one of the quantities on either of the axes in this plot, but radius is sort of a wild card lurking in the background that also affects a star's total luminosity, where it will lie along this vertical axis. However, for the sake of making a prediction, let's just be naive here and guess that all stars in the universe have the same radius. In fact, let's guess that they all have the same radius as the Sun, that every star has a radius of 1 solar radius. Now we know that that's not true. We talked about giant stars that have radii that are much larger, but for the sake of getting a prediction here, let's just ignore that. So in that case, we would expect every star in the universe to lie along a curve in this diagram, a line of total luminosity equals effective temperature to the fourth power plus or minus some constant. Now, if you have a little bit of experience plotting up various functions in a graph, then you may remember that if we were looking at an ordinary y versus x plot here, that is a graph in which the x values, the x tick mark values, and the y tick mark values were equally spaced in linear quantities, then the plot of an equation like y equals x to the fourth would give you a curved line. However, the HR diagram is a log-log plot. That is, the way these tick marks are spaced, they are uniform in increments of the log of the value along both the x and the y-axis. And in a log-log plot, the graph of a function like y equals x to the fourth will always come out being a straight line, believe it or not. Now the other thing to remember, of course, is that in the HR diagram, the x-axis, the effective temperature axis, is backwards. The x value is increasing to the left, and so we should expect a line of luminosity equals effective temperature to the fourth power to rise up as we go to the left. After all, that relationship says that as the effective temperature gets bigger, going to the left, the luminosity should get bigger as the fourth power of the effective temperature. So this line that we expect all the stars to lie upon should rise up as we go to the left. Now it just so happens that this particular HR diagram comes pre-equipped with lines indicating total luminosity varying as effective temperature to the fourth power. That's what these various black dotted lines are. And those are actually lines of y equals x to the fourth plus or minus some constant in this log-log plot. And the reason why there are a number of these different black dotted lines is because they correspond to different values of the constant that we might add to that equation, y equals x to the fourth plus or minus some constant. Now notice that we have one of these lines going right through the sun's position. So that is the line for stars that have the same radius as the sun, a radius of one solar radius. And that is what we are assuming about the radius of all the stars in the universe for this prediction. So our prediction number 2 is that all the stars in the universe should be strung out along this black dotted straight line in this diagram that's going through the sun's position. A line of luminosity varying as effective temperature to the fourth power for stars whose radius is the same as the sun. Now, if we think about the two hypotheses that we've just discussed, notice that they make two very contrasting predictions. Hypothesis number 1 predicts that stars would be scattered uniformly throughout the HR diagram. Hypothesis number 2 predicts that all stars in the universe will be strung out along a unique line running through the HR diagram. So you couldn't ask for two predictions that are more different than that. But that's good though. If two hypotheses make very different predictions, then that means that we have a way of distinguishing between those two hypotheses. Now it's time for us to put a representative sample of actual observed stars into this diagram. Now, to just give you a little sneak preview of what we're going to find that stars fall into three distinct groups in this diagram. And when we look at the full diagram, it looks kind of complicated. So we're going to take it easy by introducing these three groups into the diagram one at a time, and we're going to do so in order of the decreasing population of the group. So the first group we're going to put into this diagram will be the one whose members are the most numerous, and the last group that we'll add will be the one whose members are least numerous. So let's go ahead and put the first of these three groups into the HR diagram. So I'm going to come up here And this first group that we are going to put into the diagram is a group of stars known as the main sequence. So let me just check this box here, and that will turn on those stars. And so there they are. There is our first group of stars in the HR diagram, the main sequence. And that is the group that is the most numerous, the group that contains the largest number of stars out there. Now, in looking at this group, I'm just going to ignore these stars up here a little bit. Those are actually very hot, very luminous stars that are a little bit exotic. So let's just ignore them and just think about the stars down here, which are really the ones that make up the most of this group. So what these stars all have in common that makes them part of one group is that they lie along almost a straight line in the HR diagram, a line running from the lower right hand corner and running up to somewhere more towards the upper left. So that is a line running from the corner where effective temperature and luminosity is fairly low and running up to the region where effective temperature and luminosity is larger. So what that tells you right away, the fact that stars in this group all lie along this line, tells you that stars in this group obey an effective temperature luminosity relation. That is to say that among stars in this main sequence group, the larger the effective temperature of the star, the greater its total luminosity. And what's more, the nature of that relationship is such that when you plot these stars up in a graph of the log of the total luminosity versus the log of their effective temperature, that is a log-log plot, then the relationship is almost a straight line. Okay, I just want to address an issue with terminology here. This group of stars is referred to as the main sequence, and normally in daily life, when we use the word sequence, often we're thinking about a time sequence. We're thinking about something that changes with time. That is not what's going on here. The main sequence is not a time sequence. Stars do not move up and down the main sequence with time. Stars eventually do move around in the HR diagram as they age and evolve, but they do not do it by moving up and down the main sequence. So do not misinterpret the word sequence here. The main sequence simply refers to the fact that this is an effective temperature luminosity sequence. Okay, so the main sequence here should remind you of one of our predictions, namely our prediction number 2. In that prediction, we predicted that all stars in the universe would fall along a straight line in this diagram, and that's pretty much what stars in this group are doing. However, if we look at things in a little bit more detail here, we can see that our prediction 2 was not exactly right for this group of stars. What we said in prediction 2 was that stars should lie along the black dotted line that I'm tracing out with my cursor here. This is a line that indicates total luminosity varying as effective temperature to the 4th power. What we actually predicted is that that was the line that stars would lie along. And what we're seeing instead is that the main sequence stars lie along a line that's actually steeper than what we predicted. So what does that mean? Well, what we have to remember is the wild card in all of this, namely the star's radius. That remember, a star's total luminosity does not just depend on its effective temperature to the 4th power, it also depends on the star's radius squared, something we talked about back in episode 4. And so the fact that this main sequence is steeper than our prediction number 2 is actually telling us that among main sequence stars, stars of higher effective temperature have larger radii than stars of lower effective temperature. In other words, radius is increasing up the main sequence. And if we think about it, that would give us stars falling along a line that's steeper than our prediction number 2. That as we go up the main sequence, the luminosity of the stars is increasing for 2 reasons. It's increasing because it goes up as effective temperature to the 4th power, but then on top of that, the luminosity is increasing even more because it's also going up as radius squared, and the radius is also increasing. Okay, so that's why the luminosity is increasing faster than we predicted, and we're getting stars strung out along a line that's steeper than what we predicted because the radius is not really constant as we assumed. So what this is telling us is that main sequence stars also have an effective temperature radius relation. Higher effective temperature means larger radius among main sequence stars. And in fact, for the coolest main sequence stars, with effective temperatures down around 3500 Kelvin, their radii are only about half a solar radius. Whereas for the hottest stars, with effective temperatures up around 25,000 Kelvin or so, they have radii of 2 solar radii. And in fact, in this graph here, the relative size of the plot symbols actually indicates the relative radius of the actual main sequence stars. Now I'm just going to finish off with a little bit of vocabulary. These stars in the main sequence that have radii that are within a factor of 2 or so of the sun's radius are actually pretty small as normal stars go. And so for that reason, the main sequence stars are also known as the dwarfs. Okay, so you can think of those two terms as being synonymous, that these main sequence stars are also the dwarf stars. And then a third piece of terminology is that these stars in the main sequence are also known as luminosity class 5 stars, where 5 is written with a Roman numeral 5. Okay, that the vertical axis in the HR diagram is luminosity, and the three groups of stars we're going to talk about fall at different places along that luminosity axis, and so therefore those groups of stars are also known as luminosity classes. And this first group, the main sequence stars, or the dwarfs, are also known as luminosity class 5 stars. So all three of those terms are synonymous. Main sequence, dwarfs, luminosity class 5, we can take them as all referring to the same thing, this group of stars that we see here. And by the way, notice that our own Sun is a member of this group. The Sun is a main sequence star, which means that the Sun is also a dwarf and a star of luminosity class 5. So now that we've laid the groundwork, we can discuss the other two groups of stars pretty quickly. So let's go ahead and turn on the second group of stars that we're going to introduce. And that's a group of stars known as the red giants. So let me go ahead and check their box and turn them on. And there they are in the diagram. They've just appeared here. So this is a group of stars that lies towards the right-hand edge of the diagram. So that means that they are stars of relatively low effective temperature. And that makes sense because, as their name suggests, these are stars that are red in color. And thinking back to episode 1, that would mean that they are stars of relatively low effective temperature. That puts them towards the right-hand side of this diagram. In fact, red giants typically have temperatures, say, that are in the range from 3,500 to about 5,000 Kelvin or so. Now let's think about the vertical position of these red giant stars in this diagram, where they lie along the luminosity axis. Now a useful trick when trying to sort out stars in the HR diagram is to use the main sequence as a reference line. After all, at this point we understand the main sequence fairly well. And in particular, a useful thing to do is to think about the HR diagram in terms of vertical columns. So remembering that the horizontal axis here is the effective temperature axis, a vertical column in this diagram is a line of constant effective temperature. That if two stars lie along the same vertical column in this diagram, then they have the same effective temperature. And in particular, that means that a giant, like say this one here, has exactly the same effective temperature as the main sequence star that is directly below it. Now, even though this giant star and this main sequence star have the same effective temperature, nevertheless, the giant has a much larger luminosity. That's why it lies higher up along the vertical axis in this diagram. So we know that luminosity goes as effective temperature to the fourth power, But these two stars have the same effective temperature, even though they have very different luminosities. So how can that be? Well, we need to think about the wild card again, namely radius. A star's luminosity also depends on its radius squared, and it turns out that that's the answer here. The reason why this giant star has a luminosity much larger than a main sequence star below it of the same effective temperature is because it has a larger radius. And in fact, to account for the luminosity of these red giant stars, we infer that they have radii in the range from 10 to 100 solar radii. And hence the name giant is an apropos term. In fact, once again, the relative size of the plot symbols that are being used in this graph are representative of the relative size of the stars. Now again, a little piece of terminology here, that stars in this group, the giants, are referred to as luminosity class 3 stars. So remember, these different groups of stars lie at different values of the luminosity along the vertical axis, so they are also thought of as being luminosity classes. So we can take the term giant and the term luminosity class 3 as being synonymous. And some famous example of bright red giant stars in our sky are Arcturus in the constellation Bootes, Aldebaran in the constellation Taurus, and Pollux in the constellation Gemini. The third and final group of stars is the supergiants, and at this point we can discuss them very quickly. So that's this group of stars here, supergiants. So let me just check off their box and turn them on. And there they are. They've just appeared up here in the diagram. They lie along the top at very large values of luminosity. And once again, the same argument applies. If we look at a supergiant, like this one here, it has exactly the same effective temperature as a giant that lies directly below it, of course, because the horizontal axis is effective temperature, and yet it has a much larger luminosity. And so the only way that can be is if the supergiant star has a larger radius than the giant star below it of the same effective temperature. And in fact, the supergiants, in order to have these very large luminosities, must have radii as large as about 1,000 solar radii or so. So these are very large stars. Hence the name supergiant. Now, this group of stars, these supergiants, are also known as luminosity class 1 stars. So those two terms, supergiant, luminosity class 1, are synonymous terms. And some famous supergiants that are bright in our sky are Antares in the constellation Scorpio and Betelgeuse in the constellation Orion. And remember that this group of stars, the supergiants, is the least populous or numerous group, that these supergiants are actually quite rare stars. So at this point, we have now finished filling in our HR diagram. And let me just zoom out a little bit so we can see the big picture. So there it is. When you first saw this filled in earlier in the episode, it may have seemed very complicated and overwhelming, but I hope that after our discussion and the way we've built this up, you now find it easier to break down and appreciate what's going on here. Now, this particular HR diagram is actually kind of schematic because it was designed for teaching purposes. I just want to show you another HR diagram that's a bit more realistic in some ways. And here it is. I've just gone to the Wikipedia page on Hertzsprung-Russell diagrams. And there's a number of examples on this page that one can look at, but I'm just going to look at this first one here. Let me click on that and blow it up. And so here is another version of the HR diagram. It's got the same axes that we talked about, an effective temperature axis increasing to the left. It's got a luminosity axis increasing upwards, and these are both logarithmic axes again. And what they've done here is they've plotted up a very large number of stars using symbols of the same size, but with colors that are realistic for stars of each effective temperature. Let me zoom back out again here. So if you look at this, you can see that the three groups that we talked about earlier, there's the main sequence, or the dwarfs, or luminosity class 5. And then up here above it, we have the giant stars, luminosity class 3. And then finally at the very top, we have the supergiants, luminosity class 1. Now one more thought here actually that I'm going to introduce, thinking about these three luminosity classes, luminosity class 5, 3, and 1, or equivalently dwarfs, giants, and supergiants, you might notice looking at this diagram that the distinction between those three different classes is really only most meaningful on the right-hand side of this diagram, over here among stars that are relatively cool. Okay, that's where the main sequence stars are relatively faint compared to the giants. So there's a big difference between main sequence stars and giants over here on the right-hand side. And then in turn, the giants are distinctly fainter than the supergiants. So there's a distinct difference between the giants and supergiants over here. So on the right-hand side, those three classes are really very distinct and very meaningful. Over here on the left-hand side of the diagram, among the hotter stars, the distinction between those three luminosity classes is really less clear. That the main sequence stars are very luminous over here, and so they kind of get scrunched together with the giants and with the supergiants. So among hot stars up in this corner, it's not really so useful to think about luminosity classes 5, 3, and 1, that distinction is really more significant over here on the right-hand side among cool stars. Okay, so standing back and looking at this overall HR diagram, let's go back and remind ourselves of those two predictions that we made earlier, prediction 1 and prediction 2. Prediction 1 was the one where we guessed that stars would be uniformly distributed throughout the entire HR diagram if nature could make stars with any old combination of effective temperature and luminosity with equal probability. And clearly that prediction is not right. There are big areas of this HR diagram, such as the area here or over here, that are empty. Okay, so that's telling us that there are certain combinations of effective temperature and luminosity corresponding to this region here and elsewhere where nature does not and cannot make stars. Now thinking about prediction number 2, we might say that prediction number 2 was less wrong than prediction number 1. Prediction number 2 is where we predicted stars would be strung out along a line in this diagram. And at least the main sequence stars sort of behave that way, although as we saw, they lie along a line that's steeper than the one that we predicted because the star's radius increases up the main sequence. So standing back and looking at the whole thing here, the HR diagram is telling us something very significant. It's telling us that nature can only make stars with certain combinations of effective temperature and luminosity, namely those combinations that are populated in this diagram. Okay, that is stars that are either members of the main sequence, the giant, or the supergiant group, at least among objects that we would traditionally recognize as normal stars. And that is a profound clue to the structure of the deep hidden interior of stars, and it's also a clue to stellar evolution, how stars change as they age with time. Okay, so going back here to our teaching version of the HR diagram, a final thing that I'm going to show you that you can do that's kind of fun if you're a teacher or an instructor is you can turn on the brightest 20 stars in the sky, and this diagram will show you where they lie, and that's kind of a fun thing to do because that includes some pretty famous stars. Let me zoom in here again. So for example, there's Betelgeuse and Antares up among the supergiants, as I mentioned earlier. Rigel and Deneb are stars students may have heard of. In the giant group we have Arcturus, Capella, and Pollux. Down here among the main sequence stars, there's Procyon, there's Alpha Centauri A, so a lot of these are famous stars. Sirius and Regulus, Vega for example, uh, are all members of the main sequence. And we can also come up here and turn on the nearest 17 stars. So these are not stars that are necessarily going to be bright in the sky because they may have a very low luminosity, but they are stars that are nearby. And if we click those on, a lot of those are stars that lie down here in the lower part of the main sequence. In fact, a lot of these nearby stars are stars that are not too dissimilar for the Sun. And what's more exciting is that these nearby stars include some stars around which extrasolar planets have been discovered, such as, for example, 61 Cygnus A and Epsilon Eridani are both extrasolar planet hosts that are not too dissimilar from the Sun. Now, I really want to emphasize the usefulness of the HR diagram in practical astronomy. And this is actually something that might suggest a lab or a project that a student can do for those of you who are teachers. So let me first declutter this by turning off all these star names that I just turned on. So here's the idea, and this is a very practical situation in astronomy. Let's say we've got some unknown star whose properties we would like to determine. Let me pick on this star here again where I've placed the cursor. So the first thing that we could do is do photometry and measure the color of that star and determine its effective temperature. Right? That's something that's always straightforward and routine to do for any star, and so that gets us started. That tells us where the star lies along the horizontal axis in the HR diagram. Okay, so we can place it somewhere along this horizontal axis. Now, the other quantity that we can routinely measure for any star is the surface gravity, something we talked about in episode 3. Now you might be wondering how that's going to help us, because if we want to place this star in the HR diagram, the other quantity that we need to measure is the luminosity, not the surface gravity. But let's just put together some ideas that we had earlier in this series. Let me go back to the grayStar 3 virtual star simulator here. And you might recall that we can diagnose a star's surface gravity by doing some spectroscopy and noting the width of these individual dark spectral lines in the star's spectrum. And so if those individual spectral lines or dark lines are relatively broad, as they are here in this case, then that tells us, remember, that the surface gravity is relatively large. And if the surface gravity is relatively large, that means that the star is being compressed by a fairly strong gravitational force. So that means that the star is going to be fairly compact. It's being tightly squeezed by the force of gravity. So it's going to have a relatively small radius. And in fact, it is going to be a dwarf. So that tells us that the star belongs to luminosity class 5. And so we can put it in this group here. On the other hand, going back to grayStar 3 here, if a star has dark spectral lines that are relatively narrow, as this one does, then remember that tells us that the star has a relatively low value of surface gravity. And if it has a low value of surface gravity, that means that the star is not being very tightly compressed by gravity, that the star is able to puff up more, and so it has a larger radius. And so that tells us that the star belongs to the group of giants, or maybe supergiants, depending on exactly how narrow its spectral lines are. So by doing spectroscopy and looking at the width of the star's spectral lines, we can tell whether it belongs to group 5, luminosity class 5, 3, or 1. And remember, we also know its effective temperature, where it belongs along this horizontal axis. So all we have to do is just trace up along a vertical line until we come to the group that we think the star belongs in, 5, 3, or 1, based on the width of its spectral lines. And that allows us to place the star in the HR diagram at least approximately. So let's say it has lines of intermediate spectral lines of intermediate width, and let's say we've placed it in luminosity class 3 here. So then we can just read across horizontally to the y-axis and read off the star's luminosity, its absolute brightness. Because this HR diagram has been calibrated for us by previous generations of astronomers, so we know exactly what the absolute luminosity value is all the way up and down this axis. So now we can read off the star's absolute luminosity. Now, how does that help us? Well, if we go back to the star we're picking on, another thing we can do, of course, is we can measure its flux intercepted by a detector here on Earth, and that tells us its apparent brightness. And so we can combine knowledge of the star's absolute brightness, its luminosity, from the y-axis of this calibrated HR diagram, with the apparent brightness, the flux that we've measured for it, and by combining those two things, we can calculate the star's distance. Okay, that in this diagram, in the inverse square law, if we can measure any two things, we can calculate the third thing. So here we have gotten the luminosity, the absolute brightness, from doing spectroscopy and placing the star in the HR diagram. We can always measure the flux or the apparent brightness, and we can combine those two to get the star's distance. And that's very important because remember, the stakes are very high when it comes to measuring the distances to stars. That if we can measure the distances to lots of stars throughout our galaxy, that gives us an indication of the overall size of the Milky Way galaxy. We can use that information to determine the distances to other galaxies throughout the observable universe, and that gives us a clue to the size of the overall observable universe, an important cosmological parameter. Okay, so I hope you're starting to appreciate the big picture here and how everything fits together. Now we're coming to the end of this episode, and so it's time to talk about pedagogical activities that I can suggest based on the HR diagram. And in fact, the process that I just walked us through would be a good lab project for university students at the second or third year level. Okay, so the project where you give students photometric information about a star's color that they can use to estimate its effective temperature, where they have the star's spectrum and can look at the line width to get information about which luminosity class in the HR diagram the star is in, so that they can place the star in a calibrated HR diagram and get the luminosity from the y-axis of that diagram, and then to combine that with information about the star's measured flux in order to calculate the star's distance. That is a good solid lab project at the second or third year level in a course that's for students who are astronomy majors. Now, at a lower level, at say the high school level, or maybe the first year university level, even in a course that's for general students who aren't necessarily science majors, there's a lighter, more fun activity that I can suggest. And this is something that the class can do together or that students can work on in groups. And this is an activity that makes use of the built-in HR diagram that's in the grayStar 3 output area. So this is something I promised earlier that I would get back to at the end of this episode. So here in the grayStar 3 output, we do have a simple HR diagram, that this is the log of the effective temperature increasing to the left along the horizontal axis, and the bolometric, the log of the total luminosity and solar luminosities increasing upwards along the y-axis. So there's a little HR diagram, a relatively simple one, and in this HR diagram there are lines indicating the tracks where nature makes dwarf stars and giant stars, that is, stars of luminosity classes 5 and 3. Now this diagram does not include the supergiants, luminosity class 1. They're up here somewhere off the top of the diagram. That's because those objects are very difficult to simulate. They're not very stable, and we cannot simulate them with grayStar 3. So with grayStar 3, we're just going to be confined to simulating stars that are in the vicinity of the dwarfs and the giants. Now, grayStar 3 also plots up in this little HR diagram with an appropriately colored and sized symbol the star that it is simulating. Okay, in fact, the last star that we simulated here during our discussion was this big red giant star. And as you can see, grayStar 3 has plotted that up in the HR diagram. Now, the thing is, grayStar 3 will allow students to simulate all kinds of stars with all kinds of combinations of effective temperature and luminosity, including stars that are not in either the luminosity class 5 or the luminosity class 3 groups. That is, stars that are neither dwarfs nor giants, but are somewhere in between or above or below both of these groups. And so those are stars that nature doesn't really make or that are very rare. And so the fun activity that I have in mind, and it's really almost a bit of a game, but it's also a very informative one, is sort of like pin the tail on the donkey, except instead it's pin the star on the HR diagram. So if students start off just by setting the effective temperature and the surface gravity controls to any old values, they're probably going to make a star that isn't really one that nature makes. Like this one here, you can see that I've sort of missed the giant track, and I've also missed the main sequence track. And so that's not really a star that nature makes. And so the game for students is to see if they can play with these first two controls, the effective temperature and the surface gravity. Those are really the only controls they can play with in order to influence the position of this simulated star in the HR diagram. So can they play around with those two controls in order to hit one of these tracks, either the main sequence track or the giant track? So for example, in this case, I'm a little bit too faint. For the effective temperature that I have here, I would need to move this star upwards to higher luminosity in the diagram if I'm going to hit the giant track. And so the way I might try to do that is by turning the surface gravity down a little bit and hitting the model button. Oh, grayStar 3 is not going to let me do that. It's going to turn the surface gravity back up to 2 for me, so I might have to go down to a lower effective temperature. Okay, and let's see what's happened. Oh, and you can see I've moved the star in the HR diagram. I've actually made things worse. I've gone even further away from this track. But you get the idea that by playing around with these controls, students can see whether or not they can hit either the giant or the main sequence track. Now what's more, students can also see if they can find the values of those two settings to move the star along the giant and the main sequence tracks. And in doing so, they could actually trace out the way surface gravity and effective temperature varies along both of those tracks. And that would be kind of a fun project and an informative one. Actually, to tell you the truth, I have a feeling that this project is going to be easier to do with grayStar 3 if students just try to trace out the main sequence track here. So let me just go to the top here. I'll just hit reload. So we're back to simulating the sun, and there it is in this little HR diagram. We know for sure that grayStar 3 can follow the main sequence, so students could start with the sun, and they could see how they could play around with these effective temperature knobs, effective temperature and surface gravity knobs, in order to move the star along the main sequence here. So I've just moved the star to the left by making it a little bit hotter, and I'm now a little bit below the main sequence. So I'd have to turn down the surface gravity to make the star a little bit bigger to stay on the main sequence. So that's how one would try to play this game. Right, remember turning the surface gravity down makes the star a little bigger. So let's see how I did. Ha! Look at that. That was blind luck. There I am back on the main sequence again. So students could move the star up and down the main sequence, and they could record what the value of the surface gravity is for each effective temperature that keeps them on the main sequence, and make a little data set of effective temperature and surface gravity for main sequence stars. Okay, so as always, let me finish up here by reminding everybody of the main grayStar 3 site. And that's by going up one level in the URL. So you can get to the main grayStar 3 page where we have links to other resources, a blog, a place where you or your IT helper can download your own local installation of grayStar 3 if you don't want to rely on a connection to the server here. And at this point, I should also say congratulations, everybody. If you've made it through the first 5 videos to this point, then you've essentially completed our entire basic unit on basic stellar astronomy. Getting to this point where we can understand and appreciate the HR diagram is really the jewel in the crown of this little course. Now there's one more episode coming, and that's episode 6. And in episode 6, we're going to kind of deal with a bonus topic. In episode 6, let me run grayStar 3 here again. In episode 6, we are going to talk about what's going on in this second control panel here, which controls the surface conditions of a planet that might be orbiting our star. And we're going to talk about this thing right here, the circumstellar habitable zone, which has to do with where we could find life-bearing planets around the particular star that we've simulated, given the surface conditions of the planet that we have set. And so as you may know, this is quite a topical thing with more and more extrasolar planets being reported in the news media. So we're going to do that in episode 6, so come back for that. Thank you very much, and we'll see you next time.